In this video, I'm going to go over how to find the longest increasing subsequence given an array of integers. In the previous video, I went over the approach we're going to use, and here we're going to implement it. And I'm going to follow the same pattern I've been using for previous videos, which is I'm going to start with a top-down recursive solution, then introduce caching, then convert that to a bottom-up solution. And one more thing we're going to do is actually recreate the actual subsequence instead of just returning the length of the longest subsequence. So we're going to start with the top-down solution, which I already have written out here. And just as a quick review, we're sort of changing the question that we're asking. So we're not just asking for the longest increasing subsequence, but we're limiting that so that the last index has to be at a specific element. And so at the top level, what we're going to have to do is we're going to have to loop through and call that function on each index and keep track of what the longest actually is, and then return that value. So that's what we're doing up here. We're just looping through the array, and then helper here is going to be the actual recursive function that returns the longest increasing subsequence that ends at index I, including index I. And we're just keeping track of the longest one with this max function. And the actual recursive function, all we're going to do is for whatever index we're looking at I, we're going to check all the previous elements. That's what this loop here is. And if the number at that in the inner loop here is less than the outer element, then that means that we could extend the longest subsequence there by 1. So we have to figure out what that length is, so we make the recursive call at whatever the index j is, and then again we have to keep track of what the longest result is of all the possible values for that index. And then the base case is just when we reach I equals 0, because we know there aren't any previous elements, and so we just return 1. And this function actually does work. I'll call it for this input here. And you can see the longest increasing subsequence has a length of 4, and I think that goes 3, 5, 7, 8, right? So it ends on the second to last element. But if we change this to a bigger input, it's just going to hang. So I'll just show that. Yeah, it's not returning anything. And so what we have to do is we have to introduce caching. And we introduce caching to this problem in a similar manner as with the previous problems. At the top level of our function calls, we're just going to create a cache variable, and we pass it into the recursive function. And then from the recursive function, we effectively add another base case check to stop the recursion in case we've already solved this problem. And then at the end, we simply store the result that we would have returned before returning it, and then just make sure to pass it along to any recursive calls. And when we do this, we should have a result. Okay, and the answer for this long array is 7. And let's just make sure that it still works with the previous array. And it does, it still returns 4, so this works. Now we're going to convert this to the bottom-up solution. I kind of think this is easier than the recursive solution. The checking of previous elements I think kind of lends itself to using 2 for loops. And so all we do is we initialize the cache, we're going to call it dp, and set the base element, which is the longest increasing subsequence ending on the first element, is always going to be a length of 1, and then we start from 1 off from that and loop to the end. We just initialize it with a value of 1. That's the shortest it could possibly be. It's just the lone singular element. We then loop through, checking all the previous values. If the element that we're looking at in the inner loop is less than the current element, that means we can extend the subsequence, which means we could then possibly add this 1 value to whatever the result is for that subproblem, and we just keep track of what the longest increasing is within the cache itself. And then before we return, we have to check all the values in the cache and just return the largest one. This logic could be moved to within a single for loop, but I kind of like looping through afterwards. Kind of sort of a separation of concerns kind of thing. Although I'm sure for performance it'd probably be better in just one for loop. And so when we call this, you can see it still returns the value 4, and this would be this is the output of the entire cache. And you can see this is the largest number, which means that the longest increasing subsequence is going to end on this number 8. So the last thing we're going to do is change the problem a little bit to force us to return what the actual subsequence is, not just the length of the longest one. And I think the easiest way to do this is to just have a pointer that points to whatever the previous element is in the subsequence. And so that's what I did here. You could also just store the actual subsequence itself, although I think in the worst case that then becomes a quadratic space, whereas this is still linear. And there's another way to do it where you don't store the previous pointer, but then it becomes quadratic time in the worst case, although that doesn't really matter all that much because it's already quadratic for just creating the cache in the first place. So I'm just going to go over this the previous method. So to implement this, all we have to do is update the cache from storing just integers to, here I have a little object that saves the length, so that's the value that it would have been previously. And then we also store now a pointer called previous. In other languages, sometimes if it's not convenient to do this type of object literal thing, I've seen people just make 2 arrays. They'll make one for the length and one for the pointer to the previous element. But I did it this way. And then all we have to do is whenever we update the length to be the new longest, we also have to save the previous pointer that we came from. And with the way it's written, it's pretty easy to do that. The previous pointer is always just going to be j within the previous loop, because that's the element that we're comparing it to. And then when we loop through, finding before we were just pulling out the longest element, or the length of the longest subsequence, here we have to keep track of which index that's at, because we then have to rebuild the path. So that's what this longest end index is. And then here we're just rebuilding the path, just following the pointers basically, and we just have to go until we find a pointer that's pointing to itself, because that's when it has a length of 1. And yeah, when we're pushing these values in, they get pushed in backwards, so we also have to reverse it before we return the actual sequence. So for completeness, I want to go over quickly the way to rebuild the path if you're not saving pointers to the previous elements, but you just have the lengths of the longest increasing subsequences at each index. So I reverted the cache to just have integers. So this is the way it was before. And here we're basically just pulling out the index of the last element in the longest increasing subsequence for the whole problem. So we know that's going to definitely be the last element in the path, so we push it into the path here, and we initialize an index called cur, which points at that index. And then we have some kind of tricky logic for rebuilding the path, and this kind of feels like, to me, it kind of feels too tricky and kind of like we're solving the problem a second time, but this type of logic is actually kind of common in the more difficult dynamic programming problems, so I thought I would include it. And so basically, like I said, it's almost like solving it again. We just have to check all the previous elements from the current index that we're looking at, and we check if it's a possible candidate for a previous element, because the ending element number has to be lower than the current element number, so that's what this line is. And then we'll know that it's the previous element in the subsequence if its length is 1 less than the current one, because that would show that we increased it by 1. And so if both these things are true, then that means that we found our element, so we push it into the path, and we also update the current index. And we also don't have to continue in the for loop, so we break out of it. And we just continue doing that until we find the last element, that is the element that has the longest increasing subsequence of 1, which is just going to be the first element in whatever the longest increasing subsequence is. And like the previous solution with the pointers, we have to reverse it because we built the path up backwards. And at that point, this path is the longest increasing subsequence for the problem. So that's the way you solve it this way also.